Hi everyone, my name is Gerardo Lara, student from University of Guadalajara, pursuing bachelor's degree in mechanical and electrical engineering. And here I would like to show in this video the work I performed during this RIS 2026 edition. First, I would like to thank Carnegie Mellon University for giving us this opportunity. I would like to thank Rachel Bursin and Leon Dolan for guiding us during this program. Also, would like to thank my university, University of Guadalajara, for providing us and helping us during this research and providing us this valuable research experience. I would like to thank my lab, Robotics lab, where I perform my research. And thanks to the guidance of Howie Joseph, David Neiman, and Nico Ceballos for guiding me and giving me advice during this summer research. So here I would like to present everyone the project which is called Independent Multi-Frame Representation for Segmented Snake Robot Orientation Control, which is focused on snake robots. Uh, the motivation for this is that currently there is a necessity that the snake should be controlled by multiple controls at the same time. So currently the snake works as a whole, and we can perform different types of movements, which we are going to call gates during this video. So right now there are some situations or cases where multiple control might happen. One of the new implementations that I work on specifically is Cobra mode implementation, where it's a mode where we try to put the head from up from the ground, so the head has more like has a hemisphere of vision across like around. So for that we require a control for a neck that points the head up, a control for the head when we are doing head look, and the normal gates running on the other modules. Also, it might happen the lab is developing an anchoring mode, which consists of the last modules will be performing like an anchoring position. It will try to fix the snake in between two walls or within a pipe, and the other rest modules will be performing anchoring, reaching control or exploration control, and also we they also need the option of the head look. So for those cases, we there are multiple controls happening at the same time, and for that I propose a multi-frame representation for each of them, which is currently previous work refers to the virtual chassis, which is a representation of the whole body itself as a one, but it doesn't account for these subsets of control. So I'm proposing this extension of making multiple representation for each controller at a time. And that way we have multiple coordinate frames for each of them. We can keep track of what is going on between them. Also, we have this box representation to create an intuitive control of what the control is doing. So first of all, I split it in different boxes, so we have different better representation. Also, I propose a physical grounded axis convention, which consists of I have my snake driving, and in order to make it consistent in our reference, I define that Z should be always up, x-axis should be always alongside the snake, and y-axis will be the cross product of them, so side to side. So that way it's always moving forward and backward would mean x-axis, up should be always z-axis, and side to side will be y-axis. In order to keep that consistently, I use the concept of virtual chassis running a singular value decomposition calculation in the center of mass. I create my candidate of z-axis vector, which is in a cloud of point will be the less spread one, the less spread with one direction. I compare it to the previous direction and check that there's not many changes, and I always have my reference, which is accelerometric data, which is basically the vector of gravity. So gathering all those concepts, we create a two-stage complementary filter which tries to avoid to reduce like jittering and tries to avoid drifting over time. And we always have this convention, and the axis doesn't flip over time. So current results shows that this method applied on the real snake with real accelerometer data demonstrates that with previous chassis, our z-axis tends to flip a lot. So sometimes the z-axis is up, sometimes it's down, sometimes it's one side. In the red line, in the first plot, we see that the the angle between the z reference up and the current z-axis from the virtual chassis flips a lot. It changed a lot. So with our method, we try to aim that to 0. So that means that z-axis it's also no more than 90 degrees, and it keeps telling us if there are some disturbances, of course, but we always have the z-axis convention as we propose. Uh, Now, regarding the Cobra mode, which is the one I focus on this research, I developed the closed loop control feedback for this method. In this moment, in this scenario, I choose two modules for the neck for being actively controlled. So the head is always looking up. In this picture, you might see that this is an example how Cobra mode looks like in real life. And the second plot shows plots what's the head orientation against the accelerometer data that is pointing up. So we are expecting this angle difference to be close to 0 while we are moving the snake. So this plot shows the snake moving between different gates, which is lateral undulation, rolling, turning place, etc. So we can see that the average offset is around 43 degrees. So that means that most of the time the module is like in 43 degrees offset from the real up. That means that is all the time is trying to look up, but sometimes it cannot achieve like 0 degrees or close to 0. So it tends to be 43 depending on the snake on the gate that is going on. So that's the results I got for now. I would like to show you in a moment how this control behaves on the real snake. I have it with me, so I will show it later. But I want to mention that for this future work might include trying to add a tree module for the neck control, so we can maybe achieve more accuracy looking up, because sometimes because we are using only two modules, there are some physical limits that cannot make achievable this ratio in some specific situations. So a tree module added to the net control might be a future work. Also integrating slime simulation for tracking all the coordinate frames that I propose for each subset might be useful. So we have a 3D coordinate frame and we can check and control, check and track what is the displacement of each subset. And also a future work might be implementing this multi-representation in pipe navigation, which involves pipe climbing, pipe transition, pipe crawling. So that would be future work. Right now, I would like to show how the Cobra mode controller works in real life. So let's go. So as I mentioned before, we are going to try right now Cobra mode, which is going to consist on actively controlling this module and this module to make or to achieve this position, then where the camera has a hemisphere of vision towards like all directions, so I can look at every position I want, every location, which we cannot achieve when the snake is like this. When the snake is in this position, I can only look like those directions, but if I want to look this side, I cannot do it, right? So if we put the head look in this second floor, we can mention it like that. We have these possibilities of looking to the other sides. So essentially, um, we have the snake right now in Cobra mode, and like depending on the orientation of the data that we are getting, we are trying to achieve an up position. So for example, every time I try to rotate the snake, it will follow our vector of gravity, which is going up. And yeah, so this is the how it should behave towards when a gate is it's going on. So let's test how it looks like. uh, so for example, we can try right now, uh, let's say linear. We can try the lateral undulation, which is gonna be something like this. Then we can try some turning plates, for example, and we are expecting the head to be always looking up. um, I can try also rolling, for example. Rolling is a good example for showing the current controller. And yeah, essentially right now we are using only two modules for this control. We expect for future work to use three modules for the neck, and we might achieve higher accuracy. Right now our results are about 45, 43 degrees of offset, mean offset, according to the up reference. But maybe if we implement a third module for this, we might have better results. So for now, that's everything. Thank you so much for listening. Thank you so much, Reese and CMU, for this opportunity. I really enjoyed my time here, and yeah, thank you so much.